So if you recall, last time we ended up here, we considered two classifiers, one based on a single binary feature, the other one based on, let's say, a pair of features, but like one binary, the other one categorical with three values, like three levels, and so argue that we can view that other case again as a new categorical variable with 6 levels. And so we did our like plug-in estimate of the optimal rule by approximating the joint distribution. So if you recall, we had the joint distribution from these empirical averages, and then we do the conditional distribution, and then you can apply the Bayes rule or like optimal rule, which is threshold these conditional probabilities. That's our 1/2, and so you'd end up getting this simple picture, like some summarization, not simple, like summarization of the behavior of the conditional distribution given all the possible choices of the two variables. And so this gives you the optimal classifier as well, sort of your estimate. And so it turned out to be like this. And so this is more complicated than the original one that we had based on just say. And so we wanted to compare or say whether this is much better than the previous one. So we did calculate the test errors. For this one, it's like 0.211, and for the other one, 0.217. And so at this point in machine learning community, you're good. So this one beats the other one, so it's a better estimator. They do report error bars. So they do, if you look at research papers, they're good enough that you put an error bar around those. Okay, so it's like 0.211 plus minus a level of error, which is dependent on your, let's say, test sample size. And so basically you want to do that. And so maybe this with it, but if you consider the error and they're not that different. Okay. So that's sort of a little bit of a statistics there. So I started doing this. There are a couple of ways of doing it. The simplest way of doing it is just to recall that these test errors are just averages. So averages these indicator variable, and the indicator variable is this the indicator that your classifier output is not like you get a mismatch between the classifier output and the actual labels on the test data. So the probability of this quantity at the population level is just the risk. And so this is an empirical average, and it's just an average of a bunch of Bernoulli variables, each of which has this probability there. The probability that this is 1 is just the risk, because that's the probability there. So you're like sampling n Bernoulli variables, each with the correct probability that you want. And so, for example, so this would be if I have a random variable, like set of random variables z1 up to z, let's say m, Bernoulli, let's say p1. What you're doing is really forming this estimate p hat 1, which is the sample average of these guys. Okay, and then you can also form variance, right? Like you can compute the variance of this estimate. So what is the mean of this estimator? Let's see how many of you are really stat makers. What is the mean of the sample mean? So these are IAD. The expectation of sample mean is the population mean, right? So it's like just the expectation of one of them, which is P1. So this is unbiased for estimating P1, which is our risk. So what is the variance of this estimator? Anyone knows? So like I said, the IID. So what is the variance of the sample mean? So this is really not machine learning, it's just a statistic. So 1 over m comes out, you get ms squared, and then the variance of the sum, which is the sum of the variances because of independence. Okay, so you get m times the variance of one of them. So the entire, like in the end, you'd get there's an ms squared and there's an m, so you get 1 over m variance of z1. So if you have an IID sample, the variance of the sample mean is 1 over m, the variance of one of them. The mean is the P1, given the expectation as V1 basically. But the variance goes down by 1 over n. The entire sort of the statistics is built on the fact that the variance of the sample mean sort of goes down. Okay, so you get a better estimate, more accurate. So is this sort of, so I can, so what is the variance of Z1? Anyone knows what the variance of? One more ring here. What is the variance of the Bernoulli variable?
One times 1 minus P1.
Yes, exactly. So that's okay. I can't. So this goes here. From here, we're going to come here. And then, so basically variance of p hat 1 would be p1 times 1 minus p1 over m. And so we don't know p1, but we have an estimate, and you plug in p hat 1 here and use an estimate of the variance. If the variance is this, then the standard deviation is just the root of it. Okay, root p times 1 minus p divided by root m. And the standard error, the so-called standard error, is an estimate of the standard deviation. So you just put the p hat, this is p1. So you put p hat 1 here. Okay, now this one you can compute. Okay, it goes down like 1 over root m, but that's also there. The really 1 over root m is what matters. So this tells you how, so basically you're thinking that this p hat 1 plus minus a factor of this, that's your error. Okay. And how many m's you use to calculate it determines how small this gets. Okay, so for example, I can compute this. So you can compute it, for example, yeah, I really need more room here. So let's do it here. Yes. This is really, we had one is this entire thing. And two is this entire thing. So right, so for example, I can calculate what was the other one? Right, this one, like so let's say p hat 1 is 0.211. M, I think, was Yeah, if I believe it was. Yeah, so 327 test size. So that the size of the test data is that. Okay, so I can calculate, for example, the standard error. You guys can calculate it, right? So it's like root 0.211 times 1 minus 211 divided by root 327. Anyone can calculate this? Calculator. So 0.211 times 1 minus 0.211 divided by 327. So it's like maybe roughly 0.02. Yeah, 55, something like that. But what it's saying is like, okay, it's like plus 2.1 plus minus a factor. Let's say if I want to do like 2 standard deviation, they would be like plus minus. Either they report it as the variance, or you can say like, okay, about 2 times. These are rough calculations. 2 times, it's called the sigma hat. If I want to go to a standard deviation away, it's like about 0.4. Okay. And it's 0.4, the other one is like 0.217. So the error is like of the order of like 0.02, 0.02, just covers the other one. So the other one is like, he had 2 is like 0.217. So if it's like maybe this is maybe 0.0211, maybe plus or minus this digit, the second digit could go up or down, like by 2 or like maybe 4. So it's gonna like dominate it. So it's like we are gonna be careful with deciding that this is really better than that. Okay, because if you add like the error, this is within the range of errors of this. It's like saying, okay, I detect P1 is here, and my interval is like P hat 1 plus minus, like or plus, let's say 2 sigma hat 1, P hat 1 minus 2 sigma hat 1. So this is, we're assuming the P1 is here. So really P1 could be here, okay? And if it's here, then to be honest, you have to also like compute the, consider the fact that this also has a standard error. So maybe I'll leave it a little bit more properly. But this rough calculation tells you have to really like careful, okay? So if your sample size is, these are of the same order, so this is gonna have the same uncertainty. If you do it for this, it would be like standard error of P hat 2 would be root, it's the same kind of object by root m, and this is going to be root 0.0217, 1 minus 0.0217. So the numerator is going to be roughly the same, the denominator is roughly the same. So this is going to be also roughly 0.02. So you have this, and the other one is, there's also the P2. Yeah, so imagine this, the P2 is like similar, but again, this plus minus that. So these two intervals overlap a lot. Okay, so there's really not an easy way of saying P1 is much different than P2. So the other one's probably, we don't really know P1, where P1 is, but we know the P1 is in this interval. The other one is like slightly above this. So this is for P1, this is for P hat 2. P hat 2 is slightly above because the center is above, but sigma hat 2, P hat 2. Okay, so there's really not much confidence that they're different. So we can't tell. If you want to do it a little bit more properly, you can, for example, just look at p hat 1 minus p hat 2, and then divide by the standard error of this. Calculating the standard error of this would be a little bit tricky because these two guys are not independent. So these two variables are based on the same sample. You can actually calculate the actual estimate of the variance by considering the covariance of these two. But let's say if you pretend, for example, if you pretend that they're independent, okay, they're based on different samples, the variance of p hat 1 minus p hat 2 would be, anyone knows if they're independent? Assuming independence. If you think they're independent, the variance breaks up. Like with the variance of p hat 1 plus variance of p hat 2. Really, there's a term here minus 2 covariance of p hat 1 and p hat 2. I really don't know what this is, but we're pretending that this is 0. Exactly 0 or approximately 0. If that's the case, then this is just going to be, so under null, so under the null, you're going to assume in null that P1 is equal to P2 is equal to P, then the variance of this would be P times 1 minus P over M. The variance of this would be P1 minus P over M. So this whole thing would be 2P1 minus P over M. Okay, so the standard error would be P1 minus standard deviation would be root of this. Standard error would be an approximation. I can put, if I have an estimate of P, so under the null, I can combine everything. So under the null, because I know they have the same P, they're the same, they're nully, I can just form, for example, P hat, instead of P hat, it would be like 1 over 2M summation, let's say, ZI plus WI. WI are these guys from the other estimator. So if you do this, it turns out to be like 1/2 p hat 1 plus p hat 2. It's rather simple. So this is like a cool estimate of the P under the null. You can plug it in there, right? It's a better estimate of the variance probably. So this is still, in our case, it would be about roughly 0.021, let's say, because they match up to this, or 0.02. I mean, you can do rough calculation. The real thing that matters is this F. Okay, so you plug this in, and so the standard error would be the square root 2 times roughly 0.2. I guess it's like, okay, 0.211 plus 0.217 divided by 2. 0.211 plus 0.217 divided by 2. It's like 0.214. Then you plug it in, square root 2 times 0.214 times 1 minus 0.214 divided by 337. I believe it's like, okay, this is going to roughly turn out to be 0.032. If I haven't made a mistake, I'm not sure. Then I can say, you guys can check, but that's going to be that. And then the idea is that you can argue, this is not hard if you know about asymptotic distributions, central limit theorem. In this case, you can argue that, let's say this is basically p hat 1 minus p hat 2 divided by this standard deviation, which we're approximating. This is the truest standard deviation. This is going to converge to a normal, which means 0 and variance 1 in this distribution under the null. And so with large sample size, we're going to approximate it. So it's approximately this. And I'm plugging in the estimate of this, but that's also, you can also show this as well. Like this, I believe, is also true. The standard error, which is an approximation. This also converges to the normal. So in any case, I have calculated this. This thing turns out to be, in our case, turns out to be, the difference would be like 0.217, or yeah, P1 is 0.211 minus 0.217 divided by 0.032. What is this? 0.211 minus 0.217 divided by 0.032. Are my calculations correct? Can you do the calculation? Yeah, okay, actually correct. So it's going to be negative 0.1875, something like that. Okay. So under the null, this is approximately normal, and what we observed is like negative 0.18, something like that. So is this consistent with the null? Usually, if you're a statistician, you'd say, yeah, very good consistency with the null. But if the null is not correct, you expect it to be like 5, 6, like 2, 10. Right, so this is kind of the probability you observe something like this under a normal distribution. Like the probability you observe something which is so the probability that this is bigger in absolute value than this is large. So usually we reject it because it's quite large. So we absolutely take the absolute value and then compare it with the quantize of the norm. Right. So usually we take this if it's bigger than 1.976, then we reject. This is really not bigger than 1. So this is a little bit more proper. Yes.
You said that P hat 1 minus P hat 2 by standard error follows a normal distribution, right?
Yes.
And what is the value we calculated? Minus 0.1.
So this is the realization of this in this experiment that we have. Right. So if you repeat this, if these are random variables, right? Okay. So the random variable, as a random variable, they're going to converge to it. What it is saying is, let's say if I have a sample size m, test the data rate. You calculate it once, and then let's say it's this. The next time you calculate it, it will be something else. Next time it will be something else. You did very, very large, and you plot the distribution with the approximate. Assuming that the null distribution is correct.
And how are we inferring null hypothesis is true?
So you don't say the null hypothesis is true. You'd say if the null hypothesis is true, I'm expecting to observe this to be like if you repeat the experiment many times, you'd expect to observe that this is this looks like this when you repeat it many times. So now you observe something like this, like something here. It's very close to the bulk of the distribution, so you don't reject. If you want to be really statistical, what you'd say is, okay, I'm gonna reject. Ran out of time, like space again. So let's say side note. So we reject if let's say p hat 1 minus p hat 2 divided by standard error of p hat 1 minus p hat 2 if this is bigger than a threshold. Okay. If I reject like this, then the probability, so reject H naught if this. So that then the probability of reject H naught given like under the H naught. So you I'm going to put an H naught here. So assuming that the H naught is true, the probability you reject it is the same as the probability that your normal distribution. It means 0 is bigger than tau. So you'd set it equal to alpha, let's say a certain size. So let's say I want a 0.05, and this turns out to be like 196. So what this is saying is that the model is correct, and the null is true. Then if I reject it at this level, 5% of the time I'm going to be wrong. Okay, so not in this particular example, but if you do it many times, let's say with different samples, 5% of the time on the null you're going to reject, but like 95% of the time you're going to do okay. Okay, so this is going to be your rule that you're going to do it in experiments. Just apply this rule. So you apply it. So this is this bigger than 1.96? No. So we don't reject numbers. So that's right. You can also calculate the p-value, which is just the probability that a normal distribution is exactly bigger an absolute value than this value. This is another way of doing it. So you can say, what is the probability that a normal distribution in absolute value is bigger than this? And that would be the p-value. And if the p-value is, let's say, less than 0.05, we're going to reject. That's going to be equivalent. But in this case, the p-value would be large. The probability that normal distribution is bigger in absolute value than this. So I thought it would be like probably like around like 0.8 or something. So you're not going to. But this is good enough. So don't worry about p-value. If you know like statistics, you can also compute the p-values. It's an equivalent way of doing it. But otherwise, you just want to say it's consistent. Like intuitively, if I expect a normal distribution, I see something like this, I'm fine with it. If I see something in A here, and then the reason it's very unlikely. Yeah.
And the reason that P1 hat and P2 hat are not necessarily independent, and we have to assume that they were, is because they have the same test data, right? Like
yes,
if
exactly.
You test P1 on M1,
yes,
and P2 on M2.
Then you're going to good. You're good.
Yes,
that would be perfectly fine. Yeah. So the reason why I'm worried is that I'm using the same test data. But if I split my test data into two pieces, and then I test one on one set and the other, then everything would be fine.
And then it's the standard error is equal to the square root of 2 p hat times 1 minus p hat over n if the sample sizes are the same for the two.
Yes, exactly. Yes. And even if the sample sizes are not, I'm actually doing the calculation here, you can do it for yourself. Even if they're not, you can calculate because the variance would be the sum of the variances, then you just get p times 1 minus p divided by m1 plus p times 1 minus p divided by m2. So effectively, the mu m would be like a harmonic mean of the two. That's what happens. So it would be like this, but m would be the harmonic. Yeah, so this is a good point. So it would be safer to split your sample, but the issue is that if you split your sample, then you're less accurate. Okay, there's a bit of like split factor 2 perhaps. Maybe less accurate. So these are all interesting things if you want to like dig into the statistics of it. In this experiment, the data is like I think posted. I probably not posted it, but I'm gonna post it the data. You can do different things. You can like go calculate the selected 3.27 into 2 pieces for yourself and then calculate it. Test errors and then do this test again. The other thing is that you can actually calculate the covariance here. So you can exactly calculate this. And the way to do it is either you can calculate the covariance of the sample means, or you can just, it turns out it would be like it's enough to actually calculate the covariance of these two like individual ones. You can see it's like I can just add the covariance here minus 2. The m would turn out to be should we say it? Okay, so yeah, you can either calculate covariance at this level, So it turns out that it's going to be like 1/n and then -2 times the covariance of pair of these. And so you just have to calculate the covariance of these two objects, this and that. And these are two Bernoulli variables. The covariance of two Bernoulli variables is easy. So it's like the expectation of the product minus the product expectation. So the expectation of product is where both of them are 1. So the probability that both of them are 1. So you're going to have to calculate, like to go over your test data and see for which ones both of them make a mistake. Okay, that would be the probability that Zi is 1 and Wi is 1, which is the expectation of Zi times Wi. Minus the expectation of this times the expectation of this, which is like P hat 1 times P hat. So that one you already know, but you have to compute an extra thing, which is how many times these make mistakes at the same time. And that gives you the covariance. I'm gonna leave you think about this, but you can actually calculate the covariance here from the same data and then adjust for that. And hopefully get a better test. Yeah, but the main like idea is, I guess if you're a statistician, you're gonna figure this out for yourself at some point. Okay, the main idea is that the sample size matters. Okay, and then the errors go down like 1/√n. So this factor is going to be at most, or in general, let's say it's like not too big, like it's factor. But this is the one that is going to be determinant. And so you want to, like, the rough idea is that like 1/√m gives you like roughly the scale of 10 up to a factor of 4. So this is either when it's close to 0 or 1, this is 0, but if it's 1/2, it's maximum. When it's 1/2, it's like 1/4. It's like 1/2 times 1/2. So 1/4, and it's like 1/2. So it's from 0 to 1/2 at most. The key is like this m. And so check this, like 1/√m, just to do a rough calculation. Like maybe multiplied by root of 1/2. That's the worst case that it could be. And then just see if your differences that you observe are within the tolerance. The rough calculation for yourself. And then you can do like how to get your classifiers better. Like really. So you want these intervals to be separated or this to be very large. So when you divide it, the difference you want it to be like much bigger than this. So let's say like 2 bigger than 1.96 or negative 1.96, smaller than. Okay. Yeah.
So in the case you showed in the slides, is the testing data the same or?
Yes. You're using the same testing. So this is slightly less accurate. I actually don't know what the covariance is because it's not enough to just compute it individually. So you have to also evaluate them jointly. Okay. So go see how what fraction of the test cases they both misclass. And I haven't done it. But it's a good exercise. If you want, I can assign it as a homework problem. And you can go and check. Maybe that's a good homework problem. But sort of roughly clear. I'm assuming that if you have taken a statistics course, this should be sort of sounds familiar. Like if you're testing two proportions, whether two proportions are the same or not. It's a very classical statistical idea. Okay. I'll go a little bit in question. Comment. Okay. So we concluded that they're not maybe. So the thing is, people usually go with a simpler model if there's no reason. So this looks like slightly better classifier, but you're not sure. So maybe we'll stick with this. In practice, it's often safer to use a simpler model. So in general, when you add more complexity to the model, the training error is going to go down. Sometimes the test error also goes down, but as you can see, it's not obvious that the more complex model necessarily is always better. And so the idea of choosing between two different classifiers or two different models, and multiple different classifiers in statistics, they call it model selection. And what we did was a very simple idea of model selection. But in general, like between two models, often you can do a test. But when you have multiple models, then the pairwise testing is a problematic because so you're going to incur the penalty of multiple testing, but the other ways we're not going to go into that. This just gives you an idea that you don't want to always necessarily go with a more complex model. Okay, sounds good. Okay, let's go back to, okay, now you're going to move on to the next sort of chapter of the notes, which is, so how to deal with a continuous feature. So suppose I have a feature vector, which is in RD. So it's a d-dimensional vector. If you want, x is x1 up to xd. And again, in the simplest case, x is just a real value. So simplest case, d is 1. So I just have a scalar. X is in R. But it's not discrete. So now the question is that how can I, like, any of the things that we develop can be extended to this case. So an example in the d-dimensional case is this normal 0 and identity covariance matrix, or a uniform distribution on the, it's called the cube, the hydra cube. Like, in 2 dimensions, it's just the square in R2. And so it's like that, the coordinates are independent, uniformly distributed, and 0 to 1, this is coordinates are independent, uniformly distributed, like normal distribution, but more generally the coordinates are also correlated. This is a very simple idea. Many practical distributions, at least you can assume that there's a covariance here, for example, non-identity, because the feature is actually correlated. But in any case, this is the simplest case. The issue is that for a continuous random variable, there is this idea from probability that if I observe a sample of size n, the probability that all of them are distinct is 1. Okay. With 0 probability, I observe ties. Okay, so that's the issue. So why this is the issue? Because if you recall the classifier that we were looking at, it was doing something like this. If you remember the estimate of the regression function, so this is an approximation of eta of x, which is the expectation of y given x, which is also the probability that y is equal to 1 given x. So we're still looking at the classification. So x is binary. So our estimate was this indicator xi is equal to x, yi, and then summation I from 1 to n. Indicator xi is equal to x. Okay, so what is the problem with this estimator? So in the discrete case, if you recall what this is doing, I can also write it like this. I from 1 to n, wi of x, yi, where this is w of x. So w of x, indicator xi equal to x. And I'm going to use a different notation here. So to avoid, for j, xj is equal to x to avoid confusion with this I here. Okay, so you can write this as an average of yi's with the weights of x little x, and these are the weights. So effectively, what happens is that for a given x, you're going to look at which training data points match x, like which of the training data point has features xi's that match x, and then over those, this weight is going to be 1 over how many of those there are, and then 0 elsewhere. So we can use averaging over all the training data that share the same feature as x. So now, if I am this continuous setting where all data points are the same, this runs into it. So what would this produce?
0.
0. Yeah, so it's going to be not 0. So it's going to be basically undefined. This would be, let's say, if x is equal to not equal to any other training data point, if x is not equal to any other training data point, this is going to be 0, and this is going to be 0, so the 0 divided by 0, so this is undefined. If x matches one of the training data points, with the probability 1, there's no other training data point that matches it. So there's just 1. So this is going to be 1, and here it's going to be just that xi. So it's going to be 1 divided by 1. So it's going to be just 1. It's going to be yi. So this what this does is effectively produces this classifier. So what this does is, in the continuous case, eta of x would be basically yi if x is equal to xi. Like for some of the for some I for 1 to n in the training data, and undefined elsewhere. Basically, at all the training x's, I predict the exact yi for that, and everywhere else I don't know what to do. So this has an interesting feature. It's an example where, suppose I manage to define it, like I can define it to be like arbitrary, like maybe 1, or like flip a coin here, like so make it well defined for everyone else. So let's say flip a coin here. Flip a coin to decide whether it's 0 to 1 elsewhere. So it's going to be a well-defined classifier. It has this feature that reproduces the training data perfectly. So this is called an interpolating classifiers, interpolate. But it's probably going to be doing a poor job for anything else. And a new test data point, because of this property, is going to be guaranteed to not match any of the training data. So for new data, you're pretty sure, like for all you want, it's not going to be one of the training data, so you're going to fall here. And here, let's say you're doing something random. So you're going to have an issue. So although it interpolates, there's an example of interpolating estimator. It's an interpolation which is not very useful. So it produces the training data, but not does like something completely either unspecified or just random, say, on the a new testing. Maybe if you have time, you can come back. There are interpolating estimators that are good. So you can be interpolating and then do something reasonable outside. But this doesn't work. This idea that we had doesn't work. So what do you guys think we should do? So here's an example, for example, let me show you. An example, it's from the data set I'm going to share is breast cancer data. And so it's a tumor, it's an sample of tissue, and this column tells you whether it's not malignant or benign, like that. So let's say alignment is like Cancer. So let's call this 1. Let's call this 0. So that would be our y. You want to predict whether it's like that based on some measurements. So you're trying to set measurements, radius, and texture, mean, radius, and texture. So texture of the cells, I guess, or the mean of the radius of the cells. And so these are numerical, these are real life. So if I try to apply that classifier, I'm going to run into the issue that for this exact, let's say I'm going to predict based on this one. For this exact one, I'm going to predict m or 1, but that's also for this, but for not for the things in between, I don't know. You can imagine this is not a good classifier. So is there a way to modify this idea? Okay.
Instead of wi of x, we can write the PDF.
Can you say that again?
Instead of wi of x, we can write the density of.
Oh, the density of. Okay, interesting. That's okay. That's one way of thinking about it. So you can, okay, if I wanna like, you can think of this as a probability distribution, right? So what is this doing actually? Is it probability distribution? I thought, no, actually, it's not a probability distribution. Is it a probability distribution or not?
Isn't it a probability distribution with all its mass at one point?
Yeah, it's a probability. So that's yeah, that's the issue. So if I aggregate it, so for example, counted how many xi's match little x, right? Anyway, yeah, it's a probability distribution with all the mass at one point, which is xi. So is it possible to turn it into so there is a valid probability distribution here, which is the good probability distribution. What fraction of data, training data match each level of the features? Okay. Yeah, but that would not. Okay, so let me maybe mention that this is good. So let's say instead of trying to estimate this regression function, let's say I wanted to estimate this probability distribution, the marginal probability of x. Okay, so that we have done, it would be like 1 over n summation I from 1 to indicator xi is equal to x. So that was part of the calculation that went into this. Okay, so this is the marginal distribution. So this is like a probability mass function. As x varies, little x. So in the continuous case, I can replace it with the density of x, and then somehow I have to modify this to get an estimate of the density. Okay, but then I'm gonna, so first the question is that how should I estimate this density? And if I estimate it, this goes into the denominator here, right? So if you remember this was like the joint divided. So I can put the p hat x here downstairs. So I have to do something here. I have to estimate this is the joint, which is that, but it's on the right track. So if you, the thing that I want to discuss, that idea can be used to turn this into an estimate of the density. So that's also density estimation is like one of the other classical areas. But let's say I still have an issue with the density. Okay. So what should, like, let's go back to this because it's equivalent. So if I figure this out, I can also do the density estimation. So is there a way to fix this?
You can change the loss function.
The loss function, okay. I still like the loss function. So the loss is on the yi's. So yi's are still discrete. So remember the the loss that we look at is saying whether y hat matches y and y is binary. So I really don't need to change that. My features are different, right? But my y hat is still binary, right? So this is okay. I can change it, but it's not going to help us because that not directly affecting the feature. So the simplest idea someone came up in the previous course is that I can discretize. So if your feature is continuous, okay, I can like look at the integer part, or right. So let's say, for example, this is a very interesting idea. Is like, okay, these are real values. I can make it categorical, so ordinal. Let's say just round to 15, to 14. If I round it to 14, for example, right? I get a lot of 14, and a lot of 15 is that I can then do the average. Yes.
If the support is within one integer, you can't do that. Right?
Yes, but then you can also change your threshold. So I can, for example, say I'm going to round to within 35. Okay, so if you think along these lines, you'd see, okay, maybe proceed along this line. You say, okay, I'm going to look at x, and I'm going to consider everything that's nearby in some sense. Okay, either by rounding or by some other measure. So I'm just going to replace. So this is saying x is exactly equal to xi. I'm going to say replace this with x is approximately close to xi. And whatever closeness you want to put is going to give you an estimator. So approximately close, in the end, close or similar. Okay, distance or similarity. I'm going to say similar to xi. So what I want to do is I want to replace this weight with the indicator with some general measure of similarity. Let's say they call it kernel between xi and x. So what is this? Is any general measure of similarity. Once I replace that indicator, then we're gonna be in business. Okay. So very simple, the simplest case is perhaps to say, for example, that this is indicator that xi minus x is less than or equal to h. So if I'm looking at the univariate case, but in the general case, you put, for example, a norm here. So the norm. So the distance of xi to x is less than h is only 1. Otherwise, it's going to be 0. This is very similar to this, except that I'm allowing a tolerance of h. Okay, if you're within h of a training data point, then this is going to be 1. It's not going to be exact, but if I expand my wall, it's going to contain a lot of these points. Okay, then averaging kicks in because now I have many probably training points within, hopefully within band of size h. And yes.
The denominator in the W
right.
is still
Right. Sorry. Should be the same thing. Thank you. Okay, so this weight and then my estimator would be okay. So for example, with this one, this is sometimes called a box kernel because it looks like a box in the univariate case. So these are, you can write it as, let's say, I don't know, z and x, let's say x prime and x. It's just bivariate functions. So if you have a bivariate function that measures similarity, then you can turn it into an estimator. These are called kernel regression estimators. As we'll see, they call them Nadaraya-Watson estimators. So it's a box kernel because let's say if x prime is here, if I apply it as a function of x, it's going to be like 1 in a band of size h around x. This would be h. This would be h. So it looks like a step function, and in higher dimension, it looks like a box. Like 0 goes up. And so this is going to capture everything within h of x. Okay. So you would go, for example, here. Let's say I want to calculate the eta hat of x, where x is 14. Like my bandwidth, let's say, this is called the bandwidth. It's a parameter called bandwidth. So the bandwidth is, I don't know, 0.5. So this is saying anything, any data point it's like 13.5 up to like 14.5 is allowed. Okay, so if I go over this, this is allowed, this is not, and then this one is allowed, right? And you go down in none of these. So I have 2 data points if I was not wrong. So anything xizing 13.5 and 14.5. Right, and so I'm going to average. You get benign and you get benign. So the average like 0 plus 0 divided by 2 would be benign. Okay. So if I increase the bandwidth, so let's say h is now 1. So anything between 13 and 14 would do. So now I get a lot of things, right? So this would work. This would work. Sorry, anything between 13 and 15. So these all work. Right. So if the bandwidth is, this is for h equal 1. So I get 0, 0. Now we have malign, and sorry, this is 1. So 1, 0, 0, 0, 1, 1, 0, 0, 0, 1. So what I get is 1, 0, 2, 0, 2 1s, and another 0, another 0, another 0. So you average them and they compare to 1/2, right? So basically the majority among these would be your decision. So there are more zeros than 1s, so you classify it here. So classification by hand. So you can implement this classifier just by hand, easy. Right? Still the decision doesn't change, but you can see the effect of the bandwidth. So you average or like consider more data points or less data points. Questions? There's an immediate question on what h should be. Okay, that's the issue here. Right? It wasn't there in the discrete case. But now I have a bandwidth I can just vary which bandwidth should I choose. So that's that. And then before giving you that thing, so let's say if I the rest it's always good to plot the data. So if you can visualize in this simple case is let's say if I want to do the 2D coordinates, my x would be two features, f has two features, it's two-dimensional. And I can plot the scatter plot of these points and then color them by diagnosis. And this is the plot that I get. This is very good because you look at it and you see, okay, there is a separation. Okay, I can probably, like just even a line would do a good job of separating sort of. And so by just looking and see, you can do classification. If you look at it, everything is like meshed together, mixed up, then the problem. But we'll come back to this part. You can't do always this. So in the simpler cases, we'll do that. So that's our yeah. So these are points. Slides. Yeah. So this is sort of the summary. So you replace this guy with a similarity measure, and the way to define this similarity measure is sometimes called the kernel. The kernel has different meanings in machine learning. But general idea is a bivariate function that measures similarity. Okay. We can add more constraints on it than this, but generally it's something that measures similarity. Someone else like said that the kernel is something that a mathematician used K to denote it. Okay, that's it. So general, but it's like usually a bivariate function that measures similarity. So what are examples of these kernels? So general framework is usually these translation invariant kernels. So you start from like a base kernel. Now these kernels are invariant, so that's the discrepancy in terminology. But you start from, so for example, the box kernel would be like the base kernel would be this. And then you'd apply to, it's like in the v equal 1 is just the invariant function, and you apply it to x minus x divided by h. So this is basically saying x, this is the difference and you divided by h, so it scales it up or down. So this it just scales the difference. So that's what the bandwidth is doing. And so for example, you apply this formula with this guy, you'd see that it gives you that so k0 of x minus x divided by h is going to be indicator x minus x divided by h less than or equal to 1, which would be like indicator of x minus x less than or equal to h, which is the same thing that we did.
So in these slides, U is just this scale difference between.
You can think of it, yeah, as a dummy variable, which would then replace it with that x minus x divided by h.
And should we think about each little x and big X as like column vectors? Or
Yes, you can think of them as, so in this case, I'm thinking of them as vectors in RD, just d-dimensional vectors. If you want it to be, it's usually easier to think of them as column vectors. Yeah.
so why do you use divide it by H to scale it?
Here?
Yeah.
So you can imagine that, okay, so let's say this, let's do it the Gaussian. And I'm going to do univariate case. Actually, the K0 would be R to R. So this U is univariate. So this Gaussian kernel is U squared over 2. So if you look at it, it's just something like that. It has a sort of thing like this. The thing is, I'm interpreting it as a similarity measure. Okay, so things that are here are very similar. Things that are here are not similar. So the effect of applying this to, let's say, x minus x divided by h is that I'm gonna get, so let's say a difference of, for example, 2. In this case would be here, but the difference of like 0.1 wouldn't be here if h is 1, let's say. Okay, if h is 1, if x minus x is 2, I'm here. If x minus x is 0.1, I'm here. But if I let h to be 0.001, right, 0.001, a difference of 0.1 is going to be 10, right? So 0.1 divided by 0.01 would be 10, so I'm right here. So just the scale is like how similar, you know, like what's the resolution? Okay. So do you want to consider differences of this order to be dissimilar, or differences of, so this is saying things that of the order of, let's say, 1 are dissimilar. The difference of the order 1 is dissimilar. This saying things that are of the order of 0.001 are dissimilar. An easier way of saying it is just look at this guy. I don't know, let's call this v divided by h before applying it to the differences. This is just gonna, basically it's a Gaussian with variance, which is h, sort of. So this is gonna be like either like this, if h is small, so this is h small, or like flatter, if h is big. Right, so this is like an absolute difference, and I'm putting it on a scale. So if I'm working with like h very big, differences that are big are still similar. If I'm working with it, it's very small, the differences that are big are very dissimilar.
I guess I just got a little turned around with why you also multiply it by the 1/h.
Yes, that's a good question. So that one is why this one is that? Yeah. Okay, so for this particular Nadaraya-Watson doesn't matter because the 1/h cancels out, right? So if I apply this, so imagine this kernel, right? Use this because the 1/h outside is from like on the numerator and denominator, it just goes out. But the reason is like you want the, so this is used elsewhere. For example, it's used in the kernel density estimation as well. So the problem that we mentioned earlier, trying to estimate the PDF. If I want to estimate the PDF, I can use the same idea. And in fact, like p hat of x, we can imagine if you go back, can we do it again here? So that was p hat of x is equal to x was 1/n summation I from 1 to n. Indicator xi minus x. If I'm going to do the PDF, I'm going to replace this with that kernel, right? X and xi. And so it's going to be like 1/n. And then h goes here, right? Summation k. I guess I wrote it the other way. Xi and x. So k naught xi minus x divided by h. Okay, so here h matters. So the reason why people do this is that usually, suppose, I didn't show it here, but let's say I normalize, there's a constant here. So usually you want the k naught u du, for example, be 1. So you want the integral to be 1. And if this is 1, then the integral of this also going to be 1. So then when I integrate this thing against dx, the integral goes in. So you get 1/n. So you get 1/n times the integral of these. The integral of all of these is 1. So it's a proper density, right? So this is done to like preserve the integral, basically, right? It doesn't matter for the regression estimator because you divide and this goes away. But the same idea is used to do density estimation. Again, if you remember, it's like easy, like just replace this indicator with the kernel. But when I have a density, this sums to 1. This is a key element. If I sum over x, you easily show that the sum goes in and it's just 1. The density has to integrate to 1. And so I need to like make sure that this integrates to one. An easy way is just if each one of these integrates to one, you get one over n summation one I from one to n and one is just getting one. So in order to preserve that, I start with the kernel K naught that integrates to one and do the transformation. You can easily argue that if K naught is like that, then integral of Kx will x dx is going to be one as well. The translation doesn't matter. I'm taking like, okay, so this is in RD, or you can do it in R. It's just a formula. We go back to the calculus. This just preserves the normalization via the integral. It's a good question. But now, as a consequence, you also learned about density estimator. So this is called kernel density estimate. Density estimation. This is called, let's call this KDE if you want, or kernel density estimation. It's a non-parametric, it's called non-parametric estimator of the density, as opposed to a parametric estimation. So you can impose a parametric model, so you can, for example, assume your density is a normal and then estimate the mean and variance. This is assuming nothing. Right? Doesn't assume anything about the distribution. For that, we can solve a non-parametric estimate. Okay. Questions? So this bandwidth that you see, like this is again, the similarity need not be of this form, but this translation sort of invariant in a sense. So this obtaining things by translation, this is very common. They have been like traditionally common in statistics, let's say. And this particular one is called Nadaraya-Watson. If you do the constructed kernel of similarity like this, and the resulting like density estimator is called kernel density estimate. And you can see there is a bandwidth for both. The choice of the bandwidth matters. So at what scale I want to declare kernel and this choice of the base kernel also matter. And people talk about this, or what is optimal, what is the optimal form. But for us, it just doesn't matter as much at this point. So any reasonable kernel should work. These are some common kernels. And so if you do it, just let me show you what happens if I do it with the same thing. This Nadaraya-Watson, just with this column, if you calculate that h hat, sorry, eta hat, this guy, with the Nadaraya-Watson kernel estimate, this is the kind of plot that you get. So for different bandwidths, you can see the black one is that. So these are the two samples. So these are the ones that are classified as 0. So this is like the radius. That's one of the x's, like one coordinate is 1, 2, 3. So these x's all have 0 label. These all have label 1. And you can see that eta hat, so the transition is from 0 to 1 times. Okay, so classified everything here. So this is the regression estimate, and then we cut it at 1/2. So these are eta hat x, and then you cut it at 1/2. It tells you basically this one is saying anything below this, because eta is 0. So it's like less than 1/2. These are all classified as 0. These are all classified as positive. Whereas these guys like cut off here. So there's a cutoff. So this results basically in like a threshold. So you threshold the x's, anything below is classified as 0, anything below is 1. And you can see the difference of the difference of bandwidth. Okay. I'm going to come back, maybe talk a bit about this later, but it's worth noting that, for example, the bandwidth too large may be problematic, but once it gets smaller, it's harder to distinguish. So these are both good. There's a difference in time, but you can see the behavior of the regression function is different. So this has a lot more video. As the bandwidth gets smaller, this is another one. So this is for the Gaussian kernel. This is, I think, for the box kernel. You can see the smaller bandwidth is more video. Yeah, the red one. And the larger bandwidths are smoother. Okay, so this is an issue which is often referred to as bias variance trade-off. So this is kind of the trading off the bias for the variance. And this is something that we're going to spend some time discussing because it's an important issue. Questions? Okay, so I think we're good for today, right? Any questions? So see you next time.